Well, good morning, chemistry students. Happy Friday. Hey, it's May 8th, 2020. Man, time seems to be flying by for me. I know some of you it's dragging pretty much, but I'm busy. Hey, you can stay busy too. Learn as much as you can. You got nothing else to do. All right, learning targets for today. I can give some examples of exceptions to the octet rule. Yeah, there's always exceptions. I can use the concepts of Vesper theory and molecular geometry to name and describe the shapes of simple molecules. I hope maybe that sounds familiar to you because that was one of the same learning objectives from yesterday. So here's where we left off yesterday. We had gone through examples of all except these last two. And these last two are going to get into these exceptions that we're going to talk about. Yes, I'm expecting you to be able to look at a substance, figure out how its notation is, and then figure out its shape. Now, there's basically two ways you can do that. One, you can memorize how this goes together. Or two, you can think about these things and say, gee, this looks linear. Gee, these are pointing towards the corners of a four-sided figure. Four-sided was a tetrahedron. Get the idea? All right. So, let's get into some things. We're going to practice first. Would you please draw yourself a Lewis structure for nitrogen triiodide. That's Ni3. And then figure out the molecular geometry, that's that ABE notation, and name the shape. Pause the video and go. Welcome back. Now, I really hope you paused the video and you tried to do it because you need to practice to see where you're getting stuck. If you never practice, you don't know what you don't know. Okay? Nitrogen. Iodine, iodine, iodine. 3 single bonds, unshared pair of nitrogen. Unshared pairs on each of the iodines. This is kind of a fun molecule actually. If you mix up a little sample of this, small amounts, it kind of is this slurry in the bottom of a liquid. And if you scoop out the solid and you let it dry, it's actually a contact explosive. My high school chemistry teacher talked about how he'd whip up a batch of that once in a while and he'd leave little specks of it around. So like he had students kind of walking in the room, kind of tiptoeing in because they didn't know if they were going to step down and you were going to hear a loud snap as that tiny little piece detonated. Fun stuff. I've made up some batches and what you do is, one way you do this is you have this batch that's dried on maybe a piece of filter paper and you tape a feather to the end of a stick and you reach out and you just tickle the substance with the feather, and if it's dry, it'll blow up. Not very stable. All right, that's not what we're after. We're after the molecular geometry. All right, my central atom is the nitrogen, and I see 3 atoms bonded to it, and I see 1 unshared pair. Okay, now you could memorize that little table, but I tend to just look at or think about models. Now, this is going to be a little bit of a problem, and I would love suggestions from you as to how we can address this, because normally when we get to the end of this unit, this chapter, and for testing, I would have model kits set out that you can work with. That did not occur to me when we had our materials pickup. we have a small enough class that I maybe could come up with at least a small set for everybody to try some things. But sometimes it really is nice to be able to build a model to look at and say, all right, here's my central atom, 3 atoms bonded to it in one unshared pair. Now, when I name my shape, it's triangular, but they're not in the same plane, so it must be triangular pyramidal. One more practice. All right, we're going to work on the molecular geometry and shape of the chlorate ion. Chlorate is ClO3 with a negative charge. Now, technically, it's not a molecule, but we're talking about the shape of this around its central atom. Okay, so pause the video, write out a Lewis structure, figure out the geometry, and figure out the name. Welcome back. All right, when I see these ions like this, I'm going to count up electrons. Chlorine has 7, oxygen has 6, 6, and 6, and then that negative charge means there's an extra one. So 6, 6, 6 is 18, plus 7 is 25, 26. And if all the atoms wanted 8, that would be 32. So that means 6 electrons that I have to share. That'd be 3 bonds. Okay. Chlorine, oxygen, oxygen, oxygen. Now, chlorine, well, yeah, okay, chlorine is less electronegative than oxygen, so it fits in the middle. Chlorine is the single atom. The tip that we had on, how many bonds does it look like they make, doesn't work on this one. We got 3 bonds overall, and then I should fill up unshared pairs. And I did not do this on purpose, but maybe you can see that on our central atom, there are 3 bonded atoms and 1 unshared pair, which is the same as what we just had. I just didn't think about that close enough. We have a triangular pyramidal. I meant to give you a second one, a different one to try, but oops. All right, so let's get into some of these exceptions. We're going to look at phosphorus pentafluoride. Okay, phosphorus, penta means 5, fluoride is the ionic form of fluorine. Now, it's not an ion here, but the more electronegative element is always named in that same IDE ending. Phosphorus pentachloride would do the same exception. So, I need you just to try to remember some exceptions here. If you try to work out your electrons, it's not going to work because this does something funky. Okay, so let's just think about it for a bit. Here's a fluorine atom. It's got 7 valence electrons, and you see that fluorine really wants 1 more. And here's my phosphorus with 1, 2, 3, 4, 5. 5 valence electrons, 3 singles, and a pair. Each fluorine wants 1 more electron. There's 5 fluorines. There's 5 electrons. What if we put one of these fluorines, look at that, I'm using one of the magic tools of the whiteboard. I have the infinite cloner over here. kind of jumbled. But just wanted to get the general idea. What's the problem with this? The valence energy level includes an s orbital and 3p orbitals. That's 4 orbitals. I've got right now 5 pairs of electrons around phosphorus. 5 pairs of electrons don't fit in 5 orbitals. But here's the good news. When you look at your periodic table, let's see, boron, carbon, nitrogen, oxygen, fluorine, aluminum, silicon, phosphorus, sulfur, chlorine. You see that phosphorus is in the 3rd period of the periodic table? And in the 3rd period, in the 3rd energy level, there is a D sublevel. It's just empty. But the region of space is there. So here's what we're saying. In this situation, phosphorus could be using one of those previously empty D orbitals. And we can think of one of these electrons just shifting into that D orbital, and now we've got room for 5 bonds. Now, if I were trying to do nitrogen, nitrogen can't do a nitrogen pentafluoride because nitrogen is in the 2nd energy level. It's filling up the 2nd energy level. There is only a 2s and a 2p sublevel. There is no 2d sublevel. There would not be any more orbitals available for nitrogen to use to make more than 4 possible 4 orbitals. That's it. But phosphorus, starting in this 3rd energy level, has another orbital. Now, I'd encourage you, rewind, play that back, think it through, look at your periodic table, see if you can process that. So in the end, we got phosphorus with 1, 2, 3, 4, 5 bonds to fluorine. Each fluorine has 3 unshared pairs. So all the fluorines are happy, they've got an octet, but phosphorus has 10 electrons around it. That's why it's an exception. Okay? What would be our notation? Well, our central atom has 5 atoms bonded to it, no unshared pairs. So 5 atoms, no unshared pairs. The best way to get 5 things around a central atom, a central nucleus of sorts, is to put 3 around the middle and 1 in each end. Okay? Now, we haven't talked about a name, but you maybe wrote it down. Again, those highly creative minds that came up with these names said, hey, you know, if I look at this, I could see that there's a face there, there, and there. That'd be a triangular pyramid. But there's an upside down face there, there, and there for another triangular pyramid. Remember, I had built this little model out of paper and tape. So think about a triangle pyramid up here and a triangle pyramid down here. And so they came up with this amazing name of triangular bipyramidal. I'm not making that up. That's its name. Triangular bipyramidal. Okay, 1 exception down. Now, after doing that last one, this one should be easier to understand. Sulfur hexafluoride. Well, fluorine, that same thing again, it's got 7 valence electrons, right? It wants to make 1 more bond. It wants 1 more electron. Sulfur has 6 electrons. Gee, there's 6 fluorine that each want an electron. Wonder what's going to happen. Maybe we attach 6 fluorine each to one of these, which means we're going to need 6 orbitals, right? But sulfur is in the 3rd period. There is a 3D sub-level that's available. And so when you think about the orbitals we're going to use 3s, we're going to use 3 3p orbitals, we're up to 4, and then we're going to use 2 3d orbitals, and we're going to have 6 orbitals. So what I'm going to do is just imagine, well, 6 bonds, 6 orbitals, each going to a fluorine. And each fluorine has 3 unshared pairs. Okay, all right, geometry is pretty easy. We got A, central atom, is bonded to 6 atoms. No unshared pairs on the central atom. So what do we call AB6? If we have 6 groups of electrons, they point to the corners. Well, they point up, down, left, right, front, back. Right here, if you can see it, is an octahedron. It's a die that's used in role-playing games and things like that. Somewhere, I had made my paper tetrahedron. Somewhere I have a 4-sided die, but I couldn't find it before I was making my videos. Here's an octahedron, an 8-sided die. So if you think about it, yeah, these points are each going to the corners of an octahedron. So this shape is called octahedral. Get it? Octahedron is the shape, octahedral is the adjective. Okay? All right. Next, BeF2. If you were to follow all your rules, so I'm going to do a what if here. Maybe you don't even want to write too much down right now. Beryllium has 2 electrons, each fluorine has 7. That would be a total of 16 electrons. If they all want 8, that'd be 24 electrons. That means we got to share 8 of them. That'd be 4 bonds. And so if you put beryllium here, and a fluorine, and a fluorine, and 2 double bonds, we can make a structure that works for that. But it's not right. Here's the problem. You're going to really have to put your thinking caps on. Okay? So let's just imagine good old beryllium with 2 valence electrons. And a fluorine comes along. I'm going to change color for fluorine here so you can see the electrons. The fluorine comes along with, it's got 1 and then 3 pairs. The fluorine's got 1 and 3 pairs. Now, fluorine really wants another electron. So, yeah, it's grab and hold, and that's grab and hold. Now, imagine going from there to here. What would have to happen? Just, I'm personifying here a little bit, but you got to imagine beryllium is going to reach out and grab hold of one of those other pairs from fluorine, because that's where the other electrons are, and it's going to pull it in between them. Look at a periodic table. Beryllium is on the other side of the periodic table. In fact, we would guess, if just glancing at the periodic table, we would guess that this would be an ionic bond. Okay? Well, I guess technically when you do the numbers and stuff, it behaves like it's a covalent bond, but just barely. So beryllium is just barely holding on to this electron. So if beryllium is fighting for its life to hold on to that electron, how does beryllium reach out and try to take 2 more electrons partially away from fluorine? Remember, fluorine's a bully. Fluorine does what it wants with its electrons. If anything's going to happen, fluorine's going to take it away. So what we're saying is this just is not likely to happen. Beryllium doesn't have enough attraction for electrons to be able to pull the extra pair of electrons partway away from fluorine. And so we end up with just a single bond. Be, fluorine on each side. And the reason this is an exception, hopefully you can see, is that the beryllium does not have a full octet. The fluorine do. Hey, fluorine gets what it wants. But the beryllium don't have an octet. What would be the geometry? A, B, 2. No unshared pairs on beryllium. So AB2, we had that one before. There's only 2 groups of electrons. 2 groups of electrons are going to get as far apart from each other as possible, which is on opposite sides. That's a linear molecule. One more. And this one is similar to the last one. Boron trifluoride. So, boron, 3 valence electrons. Can you see where it's going already? Fluorine, 7 valence electrons, wants 1 more. If we make 3 single bonds, okay, fluorine's all got all the electrons it wants. Boron is short. Boron only has 6 electrons by it. But in order to go to a double bond, boron, which is barely holding on to its electrons, would have to partially take away electrons from fluorine, and that's just not happening. Okay? So we're going to have a structure where the boron just has 3 single bonds to fluorine. Doing a terrible job of drawing that. Okay. Now, 3 groups of electrons. Oh, this is A, B, 3. 3 groups of electrons trying to get as far apart from each other as possible. Got to put my model back together quick. Okay, there's 3. You see that it's a triangular shape, but now they're all in the same plane, right? So this is triangular planar. So we had 2 exceptions where the central atom has more than an octet, and we have 2 exceptions where the central atom has less than an octet. When it comes test time, I'm going to limit your test questions to just those 4 possible exceptions. Okay? Now, for homework and stuff, we may also see where we have the phosphorus pentafluoride. There is also a phosphorus pentachloride that happens. And so that's going to be the same exception way where each chlorine is attached to 1 phosphorus, and the phosphorus is going to have more than 8 electrons on it. But when it comes to test questions, these are possible for on your test. Those are the only exceptions I will ask you about. Now, are there other weird things that happen out there in the world of chemistry? Yes. But I figure if you can at least understand a couple of exceptions, that helps set you up for the future. All right, that's our notes for today. I've got some practice exercises for you. Have a great weekend. Wish the weather looked as nice as last weekend, but whatever, we'll get through it. Stay safe, take care of yourselves. I'd love to hear from you. I commented, somebody finally gave me a question, and I just love the idea of answering a chemistry question, because chemistry is my first love. Love to hear from you. Take care.